Good afternoon. Welcome to the Johnson Space Center for the STS-46 Post-Flight Crew Press Conference. This is the crew show today, so with that I'm pleased to introduce Crew Commander Lauren Shriver, and we'll let Lauren introduce the rest of his crew. Lauren.
Thank you, Jeff, and let me say thank you to everybody for being here this afternoon. The crew would like to take this opportunity to fill you in on what we feel was a very, very exciting mission. You've heard various little bites of our discussions from on orbit, and we have a lot of excitement up there. We'd like to share a little bit of that with you. We were here about a month and a half ago and told you all the things that we were setting out to do on the mission, and now what we're going to do is come back and tell you a little bit about what actually did happen. Before we do that, though, let me briefly reintroduce everybody. On my right is the pilot of the mission, Andy Allen, and of course Andy was also kind of the blue shift honcho, and they found out exactly how difficult it was to shift about 12 hours away from everybody else's work schedule, and found themselves playing tiddlywinks in the middle of the night while the rest of us got good sleep going into the flight. But they did an outstanding job, of course, during the flight. MS-1 and the first ESA mission specialist to fly on a NASA space shuttle flight, Claude Nicollier. Claude was also the primary RMS operator and Eureka system specialist. MS-2 and flight engineer, Marcia Ivins, and she did photography and EOIM and IMAX and CONCAP and just about everything else on the flight as well. MS-3 and payload commander, Jeff Hoffman, and Jeff, of course, was our primary tether dynamics person and expert on the flight, and knew a little bit about everything else on the flight, I think, as well. MS-4, our Dr. Spock and science representative, Franklin Chang-Diaz, and PS-1, Franco Malerba, the first Italian ever to fly in space, and Franco's got some words about, well, we'll have some words about the science that was actually accomplished, and his impressions of a first-time flyer in space. I think he was tickled pink, so to speak, on his experiences. So with that, what we'd like to do is, first of all, lay sort of a basic framework of the primary objectives of the mission by means of some slides, some still photographs that we took. Give us time to explain what was going on, and then we have video of actually some of the scenes that really did happen, and I think you'll see as we get into the tether operations especially, there were some pretty exciting moments up there, and we knew there would be, and we told you there would be during the pre-flight press conference, and now we have the proof. So we'll show you what that looked like, and then follow up with some final slides on some of the beautiful Earth views and some of the other crew activities that happened during the flight. So if we could have the first slide. Of course, every mission starts off with getting established on orbit. Before you can do your job on orbit, we got to go through the post-insertion phase, and before we come back, of course, the deorbit prep phase. This is our flight deck crew getting established in the post-MECO time frame, making sure everything is going to be set up properly for getting the payload bay doors open so we can begin work with our payload contingent. Next slide.
The first objective of the mission, the first major objective of the mission in sequential order was the Eureka deployment. A brief recap on Eureka. It's a scientific platform developed by the European Space Agency and built by the European industry, the prime contractor being MBB Erno in Bremen, Germany. And that platform was sitting at the back of the cargo bay, and on the second day, second blue shift day, which means about 12 hours into the flight, our task was to grapple Eureka, pull it out of the cargo bay, perform various maneuvers in order to calibrate various sensors on Eureka, Earth sensors and sun sensors, then have the remote payload operation control center in Darmstadt, Germany, perform the deployment of the solar arrays and antenna, and then release Eureka. Things didn't go exactly that way. The first portion of the deploy went very well. The grapple and the unberth from the cargo bay went well. But we, a little later, got some problems with communication with the spacecraft, payload communication with the spacecraft, so that it was only possible to command the spacecraft through ground-based sites, S-band sites, in particular Kourou in the French Guiana. So we could not command the spacecraft, either the Payload Operation Control Center or ourselves, through the S-band communication system. And we delayed one day the release of Eureka. We released finally at 1 day, 17 hours and 10 minutes, so just about 1 day late, after the Payload Operation Control Center fixed their problems, or at least temporarily fixed their problems. And after release, there was a period of station keeping that Andy Allen performed. If you want to take over, Andy.
Okay. And I see the slide up. The slide that we're looking at is the Eureka over the Kennedy Space Center. And you can see the little peninsula there where the Kennedy Space Center is. We couldn't have choreographed a better shot to show for Eureka. The sequence as it went, Claude released Eureka off the RMS, and Lauren was benevolent enough to let me do the separation burn and the station keeping, which lasted a little bit longer than what we originally had planned. But the separation burn was about 0.7 feet per second velocity change away from Eureka. It went through that real nice. We went up to 1,000 feet and stayed around 1,000 feet for about 5 hours. We relaxed a little bit of our plus or minus of 1,000 feet to let orbital mechanics take effect, and we had already started thinking about that we wanted to try to conserve as much propellants as we could for what may be one of our upcoming exciting episodes. So we were working the orbital mechanics, and this is one nice shot of Eureka. We can go to the next slide also.
Well, try to ignore that ugly-looking guy in the picture. But if you look at the top of the picture, you see a keyboard and a computer. That we call the Science Operations Control Center on orbit, and it was from that little portable computer that we conducted all of the science that was on board the cargo bay of the shuttle. And it's kind of a new application that is sort of the sign of things to come for future science operations on the shuttle, where we control major payloads really directly from portable laptop computers, and this is the example of it. We positioned it clear out of the way in the orbiter mid-deck. Originally we intended to keep it up in the flight deck, but it was real crowded up there, and we had a lot of books and a lot of other things that cluttered the space, so we moved it down to the mid-deck, and Franco and I worked on it, basically grabbing the wall and the ladder with our legs, and I think that you can see that in the next picture. Next slide.
Yeah, as a matter of fact, this was the first time that I saw the capsule flipping. Once you put yourself in a position which originally was vertical, because in the previous slide the PGSC seemed to be glued to the wall, but when I was straddling the side of the wall, the PGSC looked as if it was on a table. The software that we ran for the first time to drive the scientific experiments in the cargo bay worked beautifully. We didn't have any hiccup with it. We had also quite a few updates, as you can imagine, because the scientists on ground were going through a major replanning effort throughout the mission. They in fact managed to achieve quite a substantial amount of interesting data. They basically have proven the concept of generating power in space through this novel concept of the tether. We were going through various states of emotion, hoping that the tether would be deployed at the full length, because that was the ultimate goal. But also with the limited length that we achieved, 250 meters, we had all the instrumentations working, including the 2 electron accelerators, the one made in Italy and the one made in the US. And we have got current flowing through the tether. We have demonstrated that this circuit in space works. I think we can move to the next slide. Here is Claude.
Prior to deployment of the tethered satellite, we already activated a low-level light camera system called TOP, Tether Optical Phenomena Camera. And this is a rather versatile instrument that allows us to measure all kind of low-level light phenomena, either associated with a glow on the surface of the orbiter when it moves through the ionosphere, or air glow, the faint lights that is produced by chemical processes in the high atmosphere about 100 kilometers high, or the phenomena associated with electron beams being generated in the cargo bay in association with the tethered satellite. So even prior to deployment of the tethered satellite, we activated that camera to gather some data that we were going to be able to compare with the data we were going to gather when the satellite was deployed. So this is a view of the aft cargo bay with the camera installed on one of the overhead windows.
Finally, after about a little over 24 hours of pre-deploy science, and after the first sort of false start, which was not a successful deployment, the picture you see here is of the second flyaway attempt, which was successful out to 179 meters. As you can see in this slide, we've got about 5 meters of tether out, and if you look hard in there, you can see the tether is straight. There's no oscillatory motion. The satellite was completely stable, and the orbiter, of course, was in what we call free drift, which means that it was not attempting to hold any kind of stable attitude. We were just letting it do what it would while the satellite flew away. The reason for that was that we were a little bit uncertain as to how the large translational jet firings might affect the stability of the tether and the stability of the satellite system, in case one of those jet firings would kind of yank on the tether and therefore yank on the satellite and upset the satellite. We did not want to do that sort of thing too soon. So the idea was to let the satellite get about 10 meters away from the shuttle before we tried to do anything like that. In actuality, it didn't quite get there. Our simulations were very stable in free drift, but in the real flight, it seemed like the orbiter in the yaw direction of the boom tip took off a little bit faster than we had ever experienced during simulations. And I began to fire some of the vernier jets, our small control jets, well before 10 meters, and it turned out not to have any effect at all really on the stability of the tether. So although that was an unplanned sort of maneuver, it turned out not to have any impact. Next slide.
Well, as the satellite went out further, we started to see successively more and more motion in the tether. There was always tension in the tether as it went out through 100 meters or so, and yet there was far more wiggling, I guess, than we had sort of imagined. Of course, in the simulators, we don't see the tether moving at all with this oscillatory motion. So everything we were seeing here was new phenomena. However, the deployment continued to go out very stably. I'll review a little bit what happened. We'll see some of this footage in motion in the film, but it goes by very fast. And I have to admit that when things got the most dynamic tended to be the times that we threw the cameras aside and were just glued to the windows to make sure that we were all doing the right thing. That was sort of the watchword of this mission, do the right thing. And I think we did. At any rate, we did get out to about 180 meters. We had gone through our first nighttime pass. It was extraordinary to us how the tether almost completely disappeared at night. You could still see the satellite. We had a large searchlight which we could shine on the satellite. Occasionally we played it up and down the tether, and you could see small sections of the tether. But I remember that moment when the sun first rose on the tether. It was about 170 meters of tether out there. It was a glorious sight. Everybody sort of came to the window, and we have exclamations of joy and other things when people looked out the window at the tether in the sunlight. And then the next thing we knew, there was sort of tether flopping around in all which directions, and what had happened was that the tether had just stopped moving. We recognized very quickly what had happened. We had seen this in the simulators. We reacted. We did the right thing, and we were very pleased to see that, in fact, the whole system regained stability. That gave us time to sort of sit back together with the ground and think about what to do next. The ground came up with a plan by which we, in order to clear what we assumed to be a jam, we didn't know where, we pulled back about 5 to 10 meters of tether and then started it going out much faster than its normal rate. And you'll see quite a dramatic sequence of that in the movie, where we started basically spewing tether out all over the sky. But again, despite the intensely dramatic look of the situation, the system became stable. We were able to go all the way out. At this point, again, we thought we had a nice deployment going, but then we got out to a little over 250 meters. Once again, the system hung up. At this point, the redshift had been up for well over 20 hours. We went to bed. The blue team took over station keeping and science operations. The next day, we attempted to repeat this running start to start the deployment again. The tether did not go out anymore. We never did get the tether to go out any further. We attempted now to reel in a little bit of tether, and we found it would not reel in. At this point, we were stuck between the proverbial rock and a hard place. We couldn't go out, we couldn't come in. There were three options. We could cut the tether, which we didn't want to do. We could go out, do an EVA, and pull in the tether hand over hand. And Franklin and I were very willing and ready to do this, and I think it would have worked. The alternative was to come up with another plan, which Mission Control did, and by moving the boom in and out, we were able to free the jam, and we proceeded to retrieve the tethered satellite in a very stable manner. And you'll see, as I say, some of this footage in the movie, but it does go by very fast, so I think now you have the framework in which to appreciate it, and we can go on with the slides.
One of the optical devices we attached to the top experiment that Claude talked about was a telescope. The top experiment was really an image intensifier with some regular camera lenses at one end of it. We extended that camera lens into the telescope world, and we had basically a Celestron telescope to put at the end of that. This was quite an effort pre-flight. In order to aim the telescope at something, you needed a way to find what you were aiming with, and so we had a couple of devices you can't see built around that telescope. We put this in the window. Unfortunately, the telescope, or the satellite, never got far enough away to really use this, but Claude used it one night, I think. But this, you can't really appreciate it, takes up one entire window. Next slide.
I'm not trying out a new dance step here for the Houston Ballet. A couple of people have already mentioned that we were doing a lot of nighttime observations, and we used every trick in the book that we could to optimize our ability to see low light level phenomena, beams, glow, and all the other things that Claude mentioned. And one of the tricks we used was to try to get pre-dark adapted, so that even during the daytime, some of us would wear these dark goggles. We also had red flashlights that we wore. I think you saw a picture of Claude with his red flashlight on early. So it was often quite an amusing scene of various crew members in their goggles and flashlights traipsing around the cockpit. Next.
This mission had some significant data recording requirements that were beyond the capability of the orbiter as it presently flies. And so to accommodate those requirements, we added some additional recording, camcorder and another little high 8 recorder, which required external cabling in order to make all of that work. We were recording from 2, sometimes 3 sources, probably constantly for the entire time that the tether was out and the satellite was out. And with that, if you can imagine 7 people now clumped around all of this, it should give you a feel for what it was like during the heat of battle for the TSS operations. Next slide.
This is a picture that doesn't quite do the scene justice, but this is the glow around the orbiter when we were down in our lowest orbit. The last part of our mission was to drop down into as low an Earth orbit as we could probably get to, 124 miles, and work the EOIM experiment, which was basically a tray of different types of materials and spectrometers. And what we were trying to see there was part of the materials would give us a real good idea of some of the things that we may be able to use in future endeavors, such as space station. When we get down that low in the atmosphere, we actually get a glow around the orbiter much more predominantly than we do at a higher atmosphere. And this is a picture taken out the back window of what it kind of looked like going through this dense area, much more dense than 230 miles of atomic oxygen, and how it kind of reacted with hitting the orbiter. We were payload bay into the velocity vector here. There's a little bit of a purple beam off the side there, which is one of our jets that had just fired when we took this picture. And next slide.
Okay, I think now we're ready to, we've kind of given you an overview, taking time to explain a few of the details, because the sequences, as Jeff mentioned, pass pretty quickly in the movie. So why don't we go ahead and transition to the movie now, and we'll narrate this as we go along. As I mentioned, time flies, and we had a lot of fun all through the whole thing. First thing, of course, prior to getting ready to go is getting ready for the orange suits. All of us getting prettied up, doctored up. We didn't all need our hair braided, but here's Claude getting an initial TSS familiarization. We enjoyed going out to the vehicle in daylight. This was my first experience with that, and it was kind of nice to be able to see what was going on for the first time.
I've seen a couple of space shuttle launches from different viewing areas, and it was always very spectacular. Being on the inside even was quite a bit more spectacular. Launch countdown was about as perfect as it can get, and I apologize, we were 48 seconds late, and I was hoping that we could do it in 46 seconds, but it missed by a couple seconds. The thought that really crossed my mind more than anything else going through all of this was what it took to make all of this happen. It's hard to think about and imagine the thousands of people or the tens of thousands of people that can make all of this work. And it takes such a complex piece of machinery and make it look so simple and look so easy. It's very graceful and very easy as it goes up on his ascent. There's some shock waves that are coming as we're going through Mach 1, which is about 40,000 feet or so.
Well, this was the first of 126 space sunrises that we saw. Just soon after we got onto orbit, we opened the payload bay doors. The complement of payloads that we carried, you can see the tethered satellite up towards the front of the cargo bay, behind it the Eureka, which we soon deployed, and then the EOIM payload. So first order of business was to get the arm out and pick up Eureka.
This is the grapple of Eureka in the cargo bay. I'm approaching Eureka with the arm, and this was a view from the end effector camera, and this is the position I had for operating the remote manipulator system. At this point, I'm very close to Eureka, and I'm going to grapple it, press the trigger to grapple it, while Andy was maneuvering the orbiter, and Franco was taking pictures. It was a blue shift activity at this time. Now I'm unberthing Eureka from the cargo bay. This black structure that you see in front of Eureka are the folded solar arrays. This whole operation took about 6 hours while we were lifting Eureka out of the bay and also performing various maneuvers that as I mentioned before, to calibrate sensors. Now you see the folded solar array on one side of Eureka pretty clearly. And it's about at that point that we started having problems with payload communication. But when we were flying over some sites like Kourou, French Guiana, the ground couldn't command, for instance, solar array deployment, which you see on this picture here. Quite spectacular to see the solar array deployment. Quite a delicate mechanism also, but it worked very well. And in a few seconds, you'll see the tensioning process at the end of the solar array deployment. You see the solar array that take a stiff shape and wave somewhat, indicating a proper stiffening and tensioning of the cables that were used to deploy the solar arrays. A spectacular view of a pass over the Red Sea and the Middle East with Eureka at the tip of the arm shortly before release of Eureka. And here we go, after release.
This is coming back over the Kennedy Space Center again. We just really like this picture. The separation burn went real fine. We moved out to 1,000 feet, and we actually kept it to work over mechanics and to save a little bit of propellant. We actually worked from about 920 feet out to about 1,150 feet. And this is basically what Eureka looked like at 1,000 feet away from us. And then we did the OTM burn, which is about 5 hours later, which put it in its proper attitude. Jeff went ahead and took that picture for us, a beautiful picture of the moon going by Eureka.
Here we are setting up the Science Operations Center down in the middeck. We have this personal computer, the up-to-date technologies coming into the space shuttle too.
And now we're raising the boom, getting ready to deploy the tethered satellite. So far, everything with TSS has gone perfectly. The boom rose. When we got up to the top, we had the first difficulty. We attempted to extract one of this little umbilical at the top. It didn't pull out, so we rotated back and forth a little bit. We put it in a position where we could expose it to the sun, heat it up. Here's a nice close-up view of it. Finally, in attempting to keep it exposed to the sun, we ended up with a sight that we never thought we'd see. The TSS boom and the satellite pointed down towards the Earth. Someday on a future mission, we may actually lower a tether satellite down into the upper reaches of the atmosphere, and that'll also be very exciting. But in any case, finally, Lauren moved the whole orbiter away, and you can see the umbilical pulling. We were ready for flyaway. We had the first attempt didn't work, but finally we got the thing going, and here it is.
And this is that portion then that where the orbiter is in free drift, and the satellite, as you can see here, is moving very slowly away from the boom tip. But notice also, of course, that it is very stable. There's no tendency for the satellite to roll off or do any pitching moments, and the tether was very stable also. Each of us had an assigned task that we were doing all through the early deploy phases, and that always entailed somebody checking CRT displays up front and looking out the windows to make sure that the satellite and the tether system were in a safe configuration. We continued to fly it away. You're about 15 or 20 meters here. Notice that the tether is still very straight and very stable in this configuration. It wasn't until we got much longer lengths that we started to notice any significant tether oscillations. At about a 25-meter length, then we deactivated the KU band system for communications and converted it into a radar and started tracking the satellite so we could tell an additional means of where it was.
Now the tether is getting long enough that we started to see a lot of vibrations. This may look like a very loose tether, but there was normal tension in this tether. This is just the way a tether behaves. This is the system after we hit the first snag. It already has pretty much reached stability, and we were getting ready now to run the tether out for this so-called running start. And here it goes. You can see we were spewing tether we have probably about 20 or 30 meters of slack tether. You can see how it takes up the coiled shape that it was on the reel. But before long, the satellite keeps moving away. It pulls out the slack tether, and it's basically until we reach the next snag, it continued to move away, and even after the next snag, it basically went into a stable configuration.
I guess the next part was the red shift had been up for a pretty long day here, and we need to get them put to bed, so we put them to bed, and for the blue shift, it was pretty much watching the satellite that night. Normally, we're going to be watching about 20 kilometers and doing our normal station keeping. This is a site out the COAS, which is an optical alignment site, which is one of the ways that I could judge how the satellite was maneuvering for us. It was actually extremely well behaved, and over an 8-hour period, I never even fired a jet.
During all the on-station phase, of course, all the science instrumentations were working, and we were also watching with the top instrumentation, the satellite, which here shines against the image intensifier picture of the sky.
We weren't able, as I said, to continue the deployment. This is how you retrieve a satellite. You have to move the shuttle underneath in order to get the tether to come back in the proper place, and that's what we're about to do.
All of our operations were really conducted in a manual mode, and I think that's important to note because this system was supposed to be automatic, and it points out the value of the human being in the loop. The satellite was being controlled by jet firings from keyboards, and the tether was being controlled also from the keyboard, and everything was very smooth. The inlines were turned on a little bit later than expected, but the docking was very, very smooth.
After docking the satellite on the docking ring, we commanded the retraction of the boom, which you see here. And there was still some alignment of the satellite to perform prior to latching the satellite in cargo bay. And there was, of course, a big relief in the crew at that time.
What you see now is the ohms burn that lowered us from the 160-mile altitude down to the 128-mile altitude. And now, while we had our EOIM experiment in the bay looking at atomic oxygen, we proceeded with some different medical experiments in a little bit more relaxed time for the crew. While Jeff is doing his medical experiments, those of us that could now get to a window, who had not been able to see a window, were upstairs taking pictures. You also see in my hand there the controller that ran the IMAX camera we had in the payload bay. Now we had the opportunity to see the Earth out of the windows, whereas before we'd been looking pretty much at space, and we took advantage every time we could. We noticed one thing at 128 miles, that the Earth appears to move much more quickly past you than it does at any higher altitude, and we had the opportunity to look at 230 and 160 miles, and the Earth just smoked right by. This is Java. You can see the line of volcanoes that look like they've been laid out with a straight edge. You can also see how blue the planet looks. I mean, it always amazed me how very blue things looked.
One of the things that most interest us these days is the burning of the Amazon forest. And what you see there are little plumes of ground fires in the area of central Brazil. And then, of course, we got to be able to zoom in with a very powerful lens, and you can see some of the patches of deforestation in the state of Rondônia in Brazil. It's an area that we've been watching over and over as missions go by. And we see all the patterns of deforestation in long geometrical lines as roads and population expands into that area. We also tried to photograph the entire Caribbean basin and, of course, Brazil and Central America. We managed to get pictures of all of the Central American capitals, but we're not able to get Costa Rica because it was always cloudy over there. I guess this is a part of the
Persian Gulf.
that is the Persian Gulf,
Samoy Slick.
and a big storm. Is that Javier?
Javier.
Javier.
Is somebody else? This is Baja California, and we come on down through Central America and southern Mexico. And we're able to zoom into the city of Acapulco. I think you can appreciate the power of that lens. It's hard to it's hard to keep the camera steady when you're zooming in that close, and so you have to wedge yourself against the window. As I said, most of the area was cloudy, but we were able to get a few good shots.
This is a feel for what it would take to do a simple task in orbit, like changing the batteries in your camera. It was sometimes more than a 2-bit. We've been using the cameras a lot, so the batteries are pretty hot. But keep it, I mean, think about this. Try to change batteries one day without ever dropping a part.
And here we are playing volleyball Olympic Games, Switzerland against Italy. It's a good way of keeping in shape in space, and of course learning about dynamics in space. This is something that we ran as a way of explaining in a future audiovisual to youngsters how tethers works in space. This is the principle of angular momentum conservation, and as you see, when we elongate the tether, we have a slower rotational speed. And of course, the principal investigator of this research at the end of the experiment has the right to take advantage of the apples.
Physics works.
Well, some of us still thought it was necessary to do a little bit of work during these final couple of days. You can see we did have an ergometer on board. That was one of our medical DSOs, but Jeff still found time to play with his all-metal yo-yo there and demonstrate yet more principles of physics with that.
The PHCF, the growth hormone experiment, was their one mid-deck experiment. It required that you take it out and rotate it 5 times in 10 seconds every day. So instead of rotating the box, I'm holding the box, and Franklin's rotating me.
Well, eventually it gets time that we got to come home. And this is just Laura and I on the flight deck doing the flight control checkout. You can see some of the elevons moving there in the picture there as we check out all the flight control services. And then we put the red team to bed and make sure we're all set to go for deorbit the next morning.
When we launched, it was just about a new moon. We were up for 8 days, one day more than we had planned, and this is what the moon looked like when we finished. 126 times we got to see the moon rise and then the sun set over the payload bay, and it was just as beautiful every time we saw it. But it was finally time to come home.
By the time we were ready to come home, we knew that we were coming home either to KSC or to Edwards, so it was a simple matter of putting on the suits and getting ready to do the entry. We just didn't know where we were going to burn to for a while. But KSC cleared out. The weather, as you can see here, is only scattered clouds, very smooth air, a lot of moisture. We didn't see the condensation trails that you folks did on the ground, but it was a pleasure to fly the entry and the final approach through that nice smooth air for a change. As we come in, start to pull up about 1,800 feet and pass through 300 feet, Andy got the gear down, another major task I assigned him a long time ago, and he did a marvelous job of that. Probably much better than my subsequent landing, but it looks okay, and it really did look good from the inside as well. So we touched down there about 1,900 feet down the runway, roughly, and then rolled to a stop on runway 33 at KSC. This is really some kind of an experience here after 8 days in space, and it took us a while to want to feel like jumping up and walking around the orbiter. I remember sitting there doing switch throws and everything. That wasn't too bad, but that initial attempt to stand up was something else. Eventually, we all found our legs, though, and stumbled out of the spacecraft and had a look around. Okay, we need to go back to the slides now and pick up with some of our other activities that we didn't get a chance to show you before, and we'll start off with Andy here.
I think they shaved all the hair off my chest so I could do this, medical DSO here. Two of us, Franklin and myself, had to do what they call an intense exercise DSO, where we had to pretty much be hooked up to a lot of telemetry for EKG and heart monitoring, so the folks here on the ground and the flight surgeons could take a good look at us while we were trying to do an intense workout, trying to correlate the data that we had given them pre-flight as to how we reacted and how our hearts worked while we were up in space, and then also immediately after flight. Next slide.
We did not only wear goggles and gloves to perform the top experiment, that is to get dark adapted during the day in order to perform low-level light work during the night and to manipulate delicate filters. We also had some problems with the bathroom or the toilet or the WCS waste collection system, as we call it nicely. And we had to clear some paths that had become clogged. And we had one of the so-called fan separators. There are two of them. One of them has to work. One of them failed, and the other one showed weaknesses. So we had to do some work in order to maintain that important facility. Finally, it held until the end of the mission. We're very glad it did.
The cameras, something near and dear to my heart. We carried a standard complement of Hasselblad and Nikon and Aeroflex cameras and some camcorders, and pretty much used all of the film that we took on board. Here I'm using 2 at one time, max effort, which did make the rest of the crew very happy because I had then 2/3 of all the cameras on board. Next slide.
We start with some Earth observation views. This is a set of old volcanoes in southern Bolivia. It's in the northern Acatama Desert, one of the driest part of the Earth. You see some snow there, but I would say 90% of the time sky is clear over that part of the world. Okay, we continue our trip over South America.
Going back to the Amazon basin, this is kind of a still of what you really saw in the movie. It's more of that deforestation pattern going on in the state of Rondonia. Nothing new, but it shows how the patterns have grown over the years. Next slide. Another main objective that we had was the mouth of the Amazon River, another area kind of dear to my heart because I used to live in that area. So the entire delta is pictured in this slide, and you can see the sedimentation that is emptying into the ocean, which has grown over the course of the year. Of course, all the effluent and all the nutrients that are coming off of the rainforest as they cut the trees end up on the river and ultimately in the ocean. Next.
The blue shift, my shift, was up at work mostly when we were flying over Africa, Asia, and Australia. When we were over Africa, of course, like this slide shows, over the Sahara Desert, I was staring at the horizon to see Italy, my country. And in fact, when we were at the higher altitude for the Eureka deploy, I could definitely see Italy, and I have some pictures which are not as perfect as these, but they are much more dear to my heart. This is one of the most desert and unpopulated areas of the world. It's in the northwest part of Sudan in Africa, and geologists could tell you all the history of this land. I just like the colors and the incredible view from the sky. The next picture is the Nile and the Lake Nasser. In fact, in the top part of the picture you may see Aswan and the dam which was built some 20-30 years ago. It looks like this natural lake, which is the second largest lake in the world, artificial lake in the world, is kind of plagued by a couple of problems. First, the lack of water through the 80s, the drought that afflicted that part of Africa. And also, you notice that the left side or the west side of the lake is much more reddish than the right side. Because of the wind blowing and the sand moving, it looks like there is a lot of sand falling into the lake, therefore diminishing the overall capacity of the lake. The next picture is the Kuwait and Gulf and Arabian Sea type of environment. You see the Euphrates and Tigris rivers, and you see in the bottom part of the picture the scars of the oil well fires. These dark patches south of Kuwait City are kind of disappearing now, and observing flights over flights throughout the different shuttle missions, we have noticed that sand is slowly but surely covering up these darker patches. So in a while, possibly these cars will be disappeared.
Moving on a little bit further to the east, this is a portion of Melville Island, which is part of the Northern Territory of Australia. It's a relatively uninhabited island, but I think it's obvious that somebody is there, and they've got a fire going, most likely to burn off old pasture land underneath the open canopy trees to try to restore pasture land. You can also see a lot of sediment and silt in the coastal areas. That, in this case, is not due to erosion of the uplands like in Madagascar, because the tropical growth is still there. Most of that activity is due to waves coming on shore or tidal activity that's carrying a lot of silt and sediment back out into the shallow areas there. It's also, if you look real closely, the inland waterways are not clogged with silt, and so it's not due to erosion of the island itself. Next slide. This was, we had one very direct pass toward the end of the flight right over the top of Mount Pinatubo, and that's what you see in this picture. I think it's fairly obvious that a large portion of the top of that volcano is gone or been displaced, and perhaps you can see the gray streaks then in the rivers that lead down from that ash clogged, and then the whiter spots, if you look really close, the white areas in those rivers and those flows are the continuing washing down of new ash deposits as they continue to receive a lot of rainfall in that area. But this was relatively cloud-free, and we just couldn't pass up this shot. Clark Air Base is just directly to the east of the volcano, and of course is a deserted air base now because of that volcano. Next slide.
Well, we don't just take pictures of dirt, rock, and trees. In fact, 4/5 of the Earth is covered by water, and there's atmosphere on top of everything with lots of weather. So we do work with meteorologists and oceanographers before the flight to get sensitized to the sorts of things which they're interested in seeing. And then during the flight, we often get sent up direct messages alerting us to transitory phenomena which they'd like pictures of, such as Typhoon Janisir. Of course, we can see cyclonic storms with geosynchronous weather satellites, but from the shuttle we can provide additional information. Particularly as we fly over, we can take stereoscopic photography, which gives a good three-dimensional view of what's happening. We also, at times, this typhoon happens to have a closed eye, but there have been others where you could actually stare right down the eye down to the ocean. So it was pretty spectacular, and we enjoyed watching this storm evolve over the several days that we were able to look at it. Next slide. There's a story behind this. As I say, people send us up messages. And we got this message, this was from the oceanographers, that they'd really like us, and they gave us a certain time. They said we'd be flying over the equatorial Pacific. Just look out the window and take a picture every 30 seconds. And I remember Lauren and I were looking out the window, snap, wait, nothing. What you're looking, we were looking in a part of the ocean, the angles were such that the sun was reflecting, and we were looking in what we call the sun glint, which is able to bring out certain features. And after about 5 minutes of wait, snap a picture, wait, snap a picture, we started saying, what are we doing here? You know, what do they possibly expect us to see? And all of a sudden, bingo, this huge line. This is probably several hundred feet long. And what this is, this is a front. You can have you know, cold fronts and warm fronts not only in the air but in the water. And this is an oceanic front underwater where cold water upwelling from the bottom comes up against warm surface water. And the exciting thing is that there's a big oceanographic study effort going on in this part of the ocean right now. So they have this picture, which we were able to take, to combine with the on the ground or on the ocean data which they were taking, and so it turned out to really pay off. Next slide.
Very hopeful that somehow I'd get a chance to see Pennsylvania from 230 miles, knowing that we were in a low inclination orbit. And really, this picture is kind of it. This is a shot over Florida. We're a little bit south of Florida. You can see the Keys, some of Cuba, and some of the Bahamas. But this particular pass, the whole coastline, the whole east coast of the United States was basically visibly clear. You can follow those cloud lines, those small cloud lines, all the way up the east coast of the United States. So I was pretty happy with this pass. Next slide.
16 times a day the sun came up and went down, and each time the sun went down it was more spectacular than the sun set before it. From 128 miles, the atmosphere is noticeably thicker and more banded than it was at the higher altitudes. You can see clouds, which probably stop at 40,000 feet or so, and the atmospheric guys tell us that there's a thin band in there under the white stuff that's the debris from the Mount Pinatubo eruption a couple years ago. But we never got tired of taking pictures or watching the sunsets.
Well, you may think that this is the CDR finally enjoying a relaxing time, but actually, rather than candy-coated or chocolate-coated candy, this is gigantic tranquilizers that they were feeding me after our TSS experience, and just to get me calmed down a little bit. But, no, next slide. We really did have a lot of fun. We had a great time. We saw a little bit of everything we ever hoped to see, plus a little bit more, as you saw from the movie. Some things that we had hoped not to see. We didn't quite get to 20 kilometers of tether out in the case of TSS, but we got enough tether out to prove the concept and allow, I think, every science instrument to get a little bit of data at least. Some got quite a bit. In the interest of maybe anticipating a few questions, I thought we'd have the folks give you a brief update on things that we have learned about the successes of the mission since we got back last Saturday morning. So let's, Claude, why don't you start with Eureka and just give a little short update.
Okay. As I mentioned before, Eureka had some problems during the deploy process. As well, communication with the spacecraft, and also during the so-called OTM burn, orbit transfer maneuver burn. This burn had to be abandoned early because it was not nominal as the ground was expecting it to be. So when we left Eureka, it was in fact in a transition orbit that was unsatisfactory to perform its scientific mission. Eventually, the ground controllers in Darmstadt, Germany, were able to fix the problem, perform subsequently a satisfactory OTM burn to bring the apogee of the orbit to about 500 kilometers, at which time they fired again their thrusters in order to circularize the trajectory of Eureka. And right now it is on a stable 500 kilometers height orbit, which is a nominal orbit. They have activated nearly all of the scientific experiments on board, including an important inter-orbit communication experiments, communication between Eureka via Olympus ESA communication satellites to the Mas Palomas ground station in the Canary Islands, and this is working well. And by the end of this week, all of the experiments on board Eureka, which is finally the purpose of this whole thing, will be operating for this period of 8 to 9 months until the recovery by Flight 57 next year.
I guess, Franco, you were going to talk about some of the science.
Right, all the science instrumentation that has worked during this mission, and which, as you probably recall, is sort of 50% from Italy and 50% from the United States, 12 major investigations altogether, had their share of data during this mission. In particular, the ultimate goal, which was the one of proving the concept of driving current through this circuit made by the satellite, the shuttle, and the wire in between the two, and using the natural battery created by the movement of the wire in the Earth magnetic field, this concept has been proven. We have got to say 1 point in the curve, not the whole curve, and we are anxious to get more points with future missions. But the essential thing is there. There was a current flowing through the tether. This current was about 3 milliamps when the Italian electron generator was working. It was about 15 milliamps when the American accelerator was working, not because the American accelerator was better, the configuration was different. But these measures were confirmed both by the instruments in the cargo bay and by the instruments on the satellite at 250 meters. In addition, all the diagnostic instruments in the cargo bay and on the satellite measuring spectra of the electrons have confirmed different signatures while current was driven through the wire. So I think we have a sound set of data, which of course is not as satisfactory as it would have been if we had the chance to go out to 20 kilometers, but it's still a very remarkable point in the story, in the history of tethers in space. We have also found that the famous paint on the satellite has a very low resistance. This was an incredible project that was run in the very last weeks before launch, and I think we have to give credit to the people who took the risk of disassembling the skins of the satellite and change the paint just to have a lower resistance on the satellite external shell. Had we not done that, perhaps we would not have seen the currents that we have seen. So altogether, I would say we have a very working set of instruments for electrodynamic and dynamic experiments with tethers in space, and we are looking forward to a second chance to really do the thorough mission.
And finally, I'll say one or two things about the dynamics investigations. We stressed before this flight that this was a test flight of a new space system. And the measure of success of a test flight is how much information you got. The bottom line is we got an incredible amount of information. In many ways, we learned a lot of things that we would not have learned had the flight been completely nominal. Science investigations, every time you go out twice as far, you generate twice as much voltage. That's not the way it works in dynamics. I think you need to think about things in terms of a factor of 10. In other words, we were able to get data on many different flight regimes. The first 2 meters of deployment had a whole set of problems which we didn't know how it was going to work, and we did have a flyaway aboard in that region. And now I think we have a very good understanding of what it's like to initially deploy and the final retrieval of a tethered satellite. From 2 to 20 meters, a whole nother set of problems opens up. In order to retrieve the satellite, we knew that we were going to have to fly the shuttle underneath the satellite. And there were real questions as to whether this would cause perturbations in the satellite which might lead to instabilities. And all the test flying that Lauren was able to do to stay underneath that satellite showed that whole concept works. From 20 meters out to about 200 meters or a little bit longer, one of the biggest uncertainties in this whole system was how would the system perform with low tensions on the tether. And we showed that not only could it perform with low tensions, but even when the tether went completely slack, that we could control the shuttle and control the satellite. And that is an unexpected and very exciting result. From 200 out to 2,000 meters, we never got to go that far, but the biggest uncertainty was that's the range where you enter the resonances between the tether and the satellite. And I think we showed that the satellite control was so good and so positive that I think when we do enter that region, we'll do it with a lot more confidence than we could have done before this flight. And so it's only that final region, that last region from 2,000 meters out to 20,000 meters, which we didn't get to explore, And yet this is the region where the tension on the tether is the greatest, and where I think we had the most confidence, because that's the region that was really tested on the ground. So all in all, the most uncertain areas we were able to explore on this flight. We have a tremendous amount of data, a lot of things for people to look at. Of course, we have a lot of work to do now, and there's already a study board set up to try to determine why the tether hung up, and to make sure that we can solve the problem, so that hopefully sometime in the future it'll be possible to test this system again, and this time run it all the way out.
And Jeff, I think we're back to you.
Okay, we'll start with questions here in Houston before going on to the Kennedy Space Center. If you do have a question, raise your hand, wait for the microphone, and then identify yourself. Mark.
This is Mark from Houston Chronicle. Excuse me. Realizing there is an inquiry underway into this, in spite of that, do you have any clearer understanding this week what might have happened, what caused the last snag?
Mark, if you could hold for just a minute, let's bring the other mic over and get the question on the air for the benefit of our viewers. If you would again, please.
This is Mark from Houston Chronicle. I know there's an inquiry underway, but do you have any clear understanding perhaps this week on what caused the final snag, and are there any second thoughts about whether you might have been able to continue the experiment once you did clear the last snag?
Okay, we've got a little bit of a breakdown in our audio connection with the mics. If you guys could just very briefly summarize the question before you answer, please.
The question was that even though we have the investigation going on into to try to determine the causes of the snags or the problems in deployment that we had during the mission, have we found out anything during the week that we've been back that would point out what the causes really were? I think to try to say categorically that we know what happened would be a little presumptuous. I don't think we do, and the team is just now beginning to get a look at the actual hardware. There was a lot of, I guess, a prime contender in the first snag especially was that down in the reel, which lives down on the pallet, down in the bottom of the payload bay, that there may have been, because we're operating at such a low tension value, when it got to that point, the tension in the system was unable to pull that winding up and free it. So that's, again, that's a guess, that's not the final answer, but that may have been what stopped us the first time. When we backed up and got the running start, apparently that was enough momentum to go on through that point. And then as we slowed down to try to get back on the profile so we didn't continue to create that massive amount of slack tether that you saw briefly in the video, then we came to the second stop there at that point. And I don't think we're really quite sure at all what may have happened there. It may have been something very similar. It may have been something totally different. And then from then on, I would think we'd be really guessing after that, because we eventually got to the point where we could neither go out or in either one, and that suggests some kind of snag up in the upper control mechanism that subsequently we were able to clear out, but only after several hours of thinking by the folks on the ground who built the equipment as to what we might try to get that free. It was at that point when we could go neither outboard with the tether or pull it in, that I think the focus of everybody concerned, including us on board, I believe we sort of unanimously shifted our attention toward freeing that jam if we could, and then bringing the satellite back, either via the natural means, which we ended up doing, or using the EVA that we began to prepare for also.
Jean-Bernard Desfailles, Le Nouveau Quotidien. Mr. Shrive, you have been 3 times in the space until now. You have been last time with the Space Telescope, and it was not really a great success after the flight. Is it not frustrating to have such mission, the crew work fine, and after that somebody did a bad job, and the experiment doesn't work?
Flying in space is not a frustrating experience, let me tell you. You know, we've tried to stress, especially here, that we were involved in a test flight, and I don't think we have not really any right to expect that everything is going to go absolutely perfectly. It is always nice when it does, of course, but I think we got enough tether deployed, as Jeff explained, to investigate a really critical part of the tether envelope that really needed to be looked at. And I think we were very successful in determining that we could control a tether system at short distance. We could control the satellite as long as we have stable endpoints to the system. The tether can be doing an awful lot of fairly wild gyrations in between, and you're still basically okay with the system. So I think we learned an awful lot, even though we didn't get out to the full length. There's always a little bit of disappointment when something doesn't go exactly as planned. To go back to STS-31 for a moment, the furthest thing from my mind is that mission was not a success. I think you have the wrong slant on the Hubble Space Telescope if you think that it's not working, or if anybody thinks that it's not working. It's got some fantastic images, and the public, I hope, is getting re-educated on all the fantastic things that it really is doing, even with the aberration that it has now.
Let me add something, because I think you ask how do we feel about it, and I think what I'm going to say applies to Hubble as well as to what we just did. From an astronomical point of view, what Lauren said is absolutely correct. The Hubble has been a great success. The computers on the ground have been able to correct the aberration. The only thing it hasn't been able to do is get down to the lowest light levels that eventually it will be able to do when people go up on another shuttle flight and fix it. And what I'm trying to stress here is the extreme value of having people in space who can respond to unexpected situations. And that's what makes us feel good about our flights. Looking at this flight that we just did, when we first started working with this system, it had been designed as an essentially an automated system where you tell the tether to go up and it would go up, and you tell it to come back and it comes back. I would have felt very bad if I had devoted several years of my life to training for a flight, pushed a button to make the system work, and then it didn't work and there was nothing I could do about it. That would really be bad. But that's not what we do when we get involved in a flight. We looked at the operations. We determined that there were many areas where having people on board, we could build more flexibility into the system. And I won't go into any detail about what we did, except to say that almost every operation that we ended up doing on this tether, both to finally deploy it as far as we did and finally retrieve it, was done with purely manual operation. We basically had complete override of our automatic systems, and it worked. So the many years that we spent working on this system and developing all of this capability for people to use the flexibility that we have in space paid off. And I feel great about this, and I think everybody in the crew does.
Peter Klein from the Daily Tagesanzeiger in Zurich, Switzerland. My question goes to Marsha Ivins. This crew is a mixed crew in a variety of categories: male, female, origin, languages, Spanish, Italian, French, English. Question one, how about harmony within this family? Second, what language did your colleagues use when there were these problems with TSS, when they tried to do it again and again, 11 times, 12 times?
Of all of the apples and oranges that you described, we have one thing in common, and that's we are people. and that's all that counts among this crew or any other crew that you put together. As for your second question, everybody spoke whatever language got the point across at the time, and everybody understood what everybody else was saying.
Okay, we can come back here and take some questions afterwards, but right now let's go to the Kennedy Space Center and take some questions there. KSC, go ahead.
This is Jim Banky of Florida today. I guess a question for Jeff, perhaps. In the investigation going on here at Kennedy, will you or any member of the crew, I guess, be coming here to help or take a look at the hardware and point out anything to anybody?
I think we have a unique perspective to lend to the investigation. I think the first thing that we're going to be trying to do is to go through all of our voice records and the video records that we took, make some order in them, and make that available to the formal investigative board. And then I suspect that we'll do, well, I know that we'll do everything that we can, both in terms of looking at the hardware and reviewing some of the data to try to correlate what we saw on the spot with the things that happened from the ground's point of view, and see if we can figure this system out.
Quick follow, that means will you actually be coming here to Florida to do that anytime soon? Is that date scheduled?
It's not scheduled yet. You know, what's being done now is, I think the first formal meeting of the investigation board is this coming Monday. They have a certain amount of preparatory work to do in looking at some of the possible faults to prepare for taking the hardware apart. You don't want to go diving into the hardware and destroy evidence. So they'll do some very careful groundwork before coming down to open up the hardware. And I don't know when that will be.
And my second question for Lauren Shriver, as you came in here to Florida and the clouds were building a little bit, as you came in on the hack and around the final, did you have any problem seeing the runway, or did any time you fly through clouds and obscure your ability to touch down?
Well, we were doing a right-handed turn, and the shuttle cockpit, of course, is like a normal, fairly large airplane cockpit, and I'm sitting on the left side, so I really couldn't see the runway until at least halfway around the turn. But on the other hand, I wasn't looking for it because I knew I wouldn't be able to see it anyway, and that's an artifact of the way the shuttle is built. But it was not due to weather. I think your question was slanted toward, was there any problem with the weather? And the answer is no. I've seen some of the videos since I got back of the landing, and I know, looking at that video from the ground, it appears like the clouds were a lot more, there was a lot more to the cloud deck than there really was. It was really, from our point of view, just thin, wispy clouds that never did obscure the view of the runway or the aim point lights or anything like that.
This is Phil Chen, Earth News for Claude. It appears that in your conversations with the ground and mission control, they were treating you somewhat more formally than the other mission specialists. I'm wondering, did you have any problems as far as adjusting? Were you treated as another MS on the crew, or as somebody who is different, as a guest, and any advice you might have for the Europeans, Canadians, and Japanese who will be joining the astronaut course?
Well, I think I was treated exactly like any other MS, and they could maybe ask the question to other crew members of this flight, but I really felt I was. And well, maybe it's in my nature, I talk sparingly. That is, I speak when I feel I need to speak, but maybe not, I don't add words when I feel that it's not needed. But when I had something to say, I expressed it, and when I felt it was not needed for me to speak, I did not speak. But really, I feel that not only during this mission, but during the 12 years I was here, and during the whole mission preparation, I was considered as one member of the team here.
For Jeff or Lauren, it seemed like a lot of the problem solving to get the tether to move seemed to be almost made up on the spot. Wondering how much of this you encountered during your simulations ahead of time, and how much of it was the smart people on the ground and the smart people in the orbit figuring out how to do something on the spot.
One of the things you learn in simulations is to think on the spot. When we hit the snags in the tether, we knew what to do because we had simulated that, and it was really quite a comforting feeling. Despite the fact that there was tether moving all over the place, the tether didn't get in the way of controlling the shuttle or controlling the satellite. So we flew it like we had simulated it, and it worked great. On the other hand, some of the troubleshooting plans, that was definitely real-time reaction at its best, people coming up with new ways of doing things which we had never really dreamed of before. You think of?
Yeah, that's exactly right. Simulations, we tried to gather together a set of procedures and a way of operating that would cover anything that we might run across. And that included practicing for sudden stops of the tether, the satellite on the way out or on the way back, either one. And I think we probably used 98% of all the things we ever did in the simulator. At some point in this 24 hours of deployed operations, we exercised that. So the simulator was invaluable to us in preparing for the mission, but the actual cause then of the sudden stops and all that was took real-time analysis to figure that out and then come up with something else to try.
So Lauren, your last mission, the STS-31 set the altitude record for the shuttle, and this one during your EOIM was the second lowest shuttle mission. And can you tell us from your point of view how different it is from being on top and being on the bottom as far as seeing the Earth?
Yeah, and Marcia alluded to that a little bit. At 330 miles with the Space Telescope, that was really eye-catching in that the panoramic views, the high oblique views that we had of thousands of miles of Earth's surface at one time was really amazing, and we tried to take along cameras and lenses that would capture those views, and I think we did that. And we had the IMAX cargo bay camera as well, and it had some fantastic shots. Kind of like you get the impression, much like you do in a commercial jetliner here at 40,000 feet close to the ground. You look down and you seem to be kind of floating over the surface, and that's kind of the way it was at 330. But when we dropped down to 128, I just couldn't believe how fast it appeared that we were moving over the surface. And it didn't, it's almost like, well, how will we ever get pictures of any of this, because we won't be able to hold it, focus on one spot long enough to get the photograph. And we have IMAX again, we had the cargo bay camera again, and I think that might be a good depiction of the real difference between 330 and 130 miles. I think it's going to be interesting to look at some of those late pictures.
And for Frank or Claude, a lot of us were following the Olympics while we were following your mission in orbit, and just wondering who won the first Italian-Swiss volleyball game in space.
It was an even score, 1-1. In fact, it was a great experience to be in space with an old friend of mine, Claude, and with all the other crew members who have become also very good friends of mine. This is a great experience that I will never forget. It's also a great pride to be the first Italian in space with this satellite made in Italy, which after all has performed so well throughout the whole mission, and with all the people who have come over both at the Kennedy Space Center to see the launch and the landing. So we are really building a new culture, a new aerospace culture in Italy, which I think is really a great thing to think of.
Stefano Colezan, Aeronautica e Difesa for Franco Malerba. How did you feel, and how do you feel now about the decision to reel the satellite back in?
Well, I share very much the decision that was made. At that point, it was very unclear what would have happened if we had reeled further out the satellite. The risk of losing the satellite was very high, and the hope to manage to get the tether fully deployed was relatively slim. Plus, the satellite was running out of gas. As you know, there is a bottle of nitrogen inside, which is what makes some of the science experiments possible, and more important, helps the retrieval. Actually, Jeff and Franklin and Lauren managed to retrieve it almost without gas, but we couldn't count on it right off the bat. So altogether, it was the very rational decision to make. I think, however, that because we have gone through all this experiment, the deploy and the retrieval, we have the satellite, so to speak, ready to go. We have also a case to refly this mission.
Yeah, this was my second question. Both ASI, the Italian Space Agency, and Alenia Spazio said they have strong hopes for a TSS reflight. Is there a chance we'll see a Franco Malherba's reflight?
Well, personally, I was very happy in space. I lifted off with a little bit of anxiety as to what my adaptation to zero-G would be like and what my ability to work in that extraordinary environment would be like. Things went very well, and perhaps because I was lucky enough on the blue shift, I went to bed right away when I was in orbit, so I didn't have to work too hard when still the world looks very strange because of the zero-G environment. So now I feel like I have gained an experience which is very valuable, and also I still have this anxiety to see this experiment work in the full bloom, in the full deployed length. So I believe that first of all, we need to get this second chance, and if I had an opportunity to fly on a future mission, I would be very pleased with that.
Rob Navius, CBS News for Jeff Hoffman. From the capture bar used in the Intelsat retrieval to your deployer mechanism, we've seen some very costly equipment go through extraordinary ground testing only to betray astronauts on orbit. Is there a feeling that there may be something generic about the environment of space that may be crippling such high-tech gear and making efforts in orbit more difficult than they need be?
No, absolutely not. The problem is in the difficulty of testing on the ground. I mean, in Intelsat, I think the post-mission analysis showed that the satellite behaved exactly as high school physics would predict it would behave. The problem was that the difficulty of recreating that behavior on the ground was not sufficiently appreciated, and so the practicing that was done was not done with a system that really behaved like the system did in space. And I think the same thing is probably true, and I don't want to speculate on what the cause of the failure or the failures, because we think there were probably different things that went wrong, were on our mission. However, we always knew that the most sensitive part of this whole system, where you're reeling wires around pulleys, is when there's very little tension on the wire. If you're pulling on the wire, it stays where it's supposed to, and it's going to work. But recreating this environment on the ground where there's almost no tension on the wire was essentially impossible. We always knew that there was a regime right at the beginning of the deployment and the end of the retrieval process where we were in untested territory. We designed, I say we, the system was designed so that we thought it would work, but obviously we're smarter now, and we've got to figure out how in the future we can properly test equipment. And that's an important thing I think we're getting out of both these flights. When we're doing fundamentally new things, we've really got to pay close attention to how we're doing the testing on the ground, else we're going to continue to get surprised.
This is Marcia Dunn with the Associated Press for Jeff Hoffman. I'm wondering how the silver bullet worked, how you incorporated it into the educational video, and did you get to try any tricks on orbit? What you saw in the movie was about what we got. We were pretty busy on this flight, as you could see. You know, on my very first flight, we did, I think, a very nice educational sequence on toys in space, and I think the yo-yo was one of the stars of that show. This was, for me, I think, a little bit of nostalgia, as well as the fact that it was fun.
That wraps up our questions at the Kennedy Space Center. We can come back and entertain a few here before wrapping up if we have any.